In our previous video on recursively defined set, we introduced, as an example, the binary palindrome strings. Today we're going to prove that the set is uncountable. Let's recall what is the definition using this recursively defined grammar here. So here is either an empty string or single digit of 1 or 0, or based on some existing string, you put 1 or 0 on both ends. So this would be the grammar to generate all the palindrome strings. For example, there's something like this. Okay. For epsilon here, meaning is an empty string that is in the set. 0 is also in the set, 1, and 0, 0, 1, 1, 0, 1, 0. This is the reverse of the string equals the string itself. That's what we call palindrome here, right? So now here we want the proof is uncountable. Now, of course, we want to review what is the concept of countable versus uncountable. Usually we claim a set X is countable, infinite, if there exists a bijection function from natural number to the set. Okay, so bijection f is called an enumeration of x. So if you can enumerate this infinite number of elements in the set, then the set is countable. Of course, when we deal with finite set, if the number is finite, then it's always countable, right? So we say x is countable, the set x is countable, either it is finite or it is countably infinite, that is, have this bijection here, right? So one common example is that integer set, the set of integers, including negative numbers, that is countable. Okay, so z is countable. How do we prove that? We need to construct a bijection f. For the bijection either from natural number to z or z to natural number. So let's define f from integer to natural number as follows. Okay, so you can verify offline maybe that this function is indeed one-to-one and onto, that is bijection function. Okay, what is the inverse for any integer n? What is for the natural number n? What is corresponding? It's the inverse of this function with the corresponding value of the z, right? It turns out to be this. The first element is 0 when x equals to 0, and if this is 0th position, this is 1st position, 2nd position, 3rd, 4th. At every even position, you have positive numbers, right? The position number divided by 2. Okay, so for example, the inverse of this would be n divided by 2, right? And as odd position would be negative numbers. Okay, so that's a enumeration of z, and z is countable. Other famous example including any tuples of numbers would be countable. Now the rational number, which is a ratio of two integers, is thus also countable. Now, what is uncountable? Of course, earlier we mentioned countable meaning is either finite or countably infinite. Okay, so uncountable means we're only dealing with the set that contains infinite number of elements, because if it's finite, it's always countable. Okay, so let's review the concept here. Uncountable. How do we show a set is uncountable? You probably want to review some of textbook examples. We're not going to cover details here, but the famous approach is Cantor's diagonal argument. Okay, so that is a way, a proof by contradiction. We're going to show an example of that. Okay, and there's some other proof techniques to prove a set is uncountable. Use this theorem here. What it's saying that for a set that contains infinitely many elements, the following three conditions are equivalent, meaning if you have condition 1, you can derive to 2 and vice versa. Okay, so here we said for number 2, we said if there is a surjection, surjection, recall that this function is onto the the domain here. If you can map this set X onto U, that is, for any element in U, you can find the X such that this function f will map X to U. Okay, then the set U is uncountable, right? Based on an existing uncountable set X. Okay, so and or the other way, if it's injection, okay, injection is kind of one-to-one from U to X for some uncountable set U, then your X is uncountable. Okay, so that's kind of the common techniques to proving on the cardinality of a set. Okay, so go back and review some textbook example on that. All right, so here we want to prove the binary palindrome strings, the set of that is uncountable. Of course, we assume the length is not finite, that is the infinite number of elements in this set, because recall earlier, if it's finite, then it's countable, right? So how do we prove that? We're going to show both approaches. Okay. In order to facilitate the proof, we want an encoding mechanism to represent the binary string. Okay. So what we choose to do here is to notice that for a palindrome string, because the part it repeats in reverse order, so there's redundant information here, right? Like for example 0 1 1 0, you only know 0 1 here, okay, and the other one just reverse order with that, prepend that. Okay, so what we do is we take the prefix of the string. Okay, so this is our encoding. So what we do is, for example, we call this prefix. From this prefix, you can generate palindrome by what? By reverse it and put it at the end of it, right? So, but then there are 3 strings that are kind of a palindrome with this prefix. One is that you can just flip over, reverse it, and put them together. That's palindrome, generated by this prefix, right? Or you can put 0 in the middle, right? So in the first case, there are even number of digits. In here, you have odd number of digits, and kind of mirror, here. So that's a palindrome also. Or you can put 1 in the middle, right? So the 3 cases. What we're saying that we're going to encode this string using symbols, right? So that I don't have redundant information here. I'm going to use the prefix string 0 1 0 1 1. I'm going to prepend with either A, B, C, D. What's the meaning of the A, B, C, D? It represents different cases. If it's A, it represents this case, right? B, the second case. C will be the third case. What is D? I'm going to explain later, right? So with this encoding, for this palindrome string, we encode it as the highlighted here, 0 1 0 1 1 A, meaning this is going to be the prefix string. A meaning you just flip over and then concatenate 2 strings here. B means you're going to put 0 in the middle and then flip over and then combine. And C means you're going to put 1 in the middle, right? So what's a D? So D is the case for the empty string, or for a single string 0 and 1, right? That's kind of a trivial case. We don't care too much about that. Okay. So why do we need this encoding? This is to make the argument easier. Okay, you're going to find it out later. Okay, for the proof. Okay, so with this encoding, right? So encoding meaning any string here in the set can be encoded with this without ambiguity. All right, so you can verify that offline. All right, so let's start with the proof. Now, Cantor's diagonal argument, right? So let's do that. So in here, this is a typical proof, right? So you assume, because this is a proof by contradiction, right? So first you assume it is countable. Then earlier we know that if it's countable, then we have an enumeration scheme where you have a bijection function map, integer n to this element here. Now this element is our encoding, right? So if we assume that is the case, then you can enumerate in a certain pattern, right? For all the elements, even though there are infinite many, right? So here all the S is without encoding, which means it has some prefix, a bunch of 0 and 1s, right? So what we do here is we claim that once you have settled on this arrangement of infinite many, because they're countable, so you can arrange that with proper mapping. Now we can find another element in the set that cannot be in your enumeration. All right, that's the whole point of the diagonal argument for the proof. This is a proof by contradiction. You assume it's countable. Then how do we define that string S? Okay, so you can construct another instance in the palindrome, set, right? How do we define S? Okay, we define the S. We look at the S1 because it's a bunch of 0 and 1s, right? If the first digit of S1 is 0, then the S, we're going to make it to be 1. Okay? And then for the second digit, we're going to look at the second element in your enumeration. Okay? And make it different. Okay? So in the first case, if it's 1, we're going to be 0. If it's 0, it's going to be 1. And then we move on for the second digit. The rule is the same, right? For the second digit, if it's 0, if S2 is a 0 in your enumeration, then I choose S to be 1 digit. And then if it is 1, I choose 0. Always reverse that. So which means we continue the process. Okay. So think about it. In that case, the S is different from any element in your enumeration. Okay. So in other words, S cannot be in your enumeration because the way we construct it. But however, you claim you do have an enumeration for this set. We have constructed an element not in your enumeration. That would be a contradiction. Okay, that's proof by contradiction. Okay, so S, as we constructed, contain a prefix string that is not the same as any string on your enumeration list. So which means the set of binary palindrome is uncountable. Okay, this is identical to the textbook argument. Let's move on to the second proof. When we review that earlier, we said we have this theorem, right? So another proof approach is we can find the surjection function f, from x. In our case, x would be the set of palindrome binary strings, right? U would be some uncountable set we know for sure, right? In this case, we're going to choose the famous U, the open interval 0, 1. Okay, again, this is a textbook example to prove that this is uncountable. So U we know for sure is uncountable. So we define f so that it maps to this. And then we need to argue that this function is onto, it's a surjection, right? So how to define that? That's easy. So for any string in the binary palindrome, what we do is we look at the prefix, right? Okay, so if the prefix, for example, is 0, 1, 0, 1, 1, 1, right? We're going to map to a binary number, but this is a binary decimal number. We're going to put 0 dot in front of it. So that will be representing a number in binary representation. If you convert to a decimal, it's going to be smaller than 1, and greater than 0, and it's going to be in this interval, right? Always. Now, we want to show this mapping is onto, meaning for any real number in this range, you can always find an element in your palindrome string. Yeah, of course. How do we prove that? For any element, it must have a binary representation, right? So if you take the binary representation, and we can just take that as a prefix string in a palindrome, and we can generate either by putting A, B, C, that meaning you either reverse it and concatenate it, or reverse add a 0 in the middle, or add a 1 in the middle, right? So you can always find x. For example, if I define x like this, right? Then by our definition, fx would equal exactly y, okay? Equal this number. So we have proven that the way we construct it is a function that is onto surjection, from x to this u, which is open interval, we know that in the real number open interval, that's uncountable, right? So with that, we have the proof. Okay, so we introduced two different proofs, and that's very common for any other proof. Okay, next time when you want to prove something is uncountable, you probably want to refer to these two examples. All right, so hope you follow the steps here. I think and that's a very commonly used method. It's very useful. This is just another kind of sideline of the sequence of videos on what is called a recursion and recursively defined set and other recursion relation and some recursion algorithm in combination of math and CS. Okay, so hope you're gonna subscribe to the channel and check out the future videos in this area. All right. Thank you for your support.